Hey, and welcome to The Explainer. Today, we're going to talk about a word you hear constantly, maybe without even thinking about what it really means: voltage. We're going to pull back the curtain on the invisible force, this hidden landscape that gives the whole idea its power. All right, let's get into it.
So think about it. You plug in your phone, you check a battery, you see those big warning signs, high voltage. But what are we actually measuring? Like, what is a volt? What does that even mean? Well, to really get it, we've got to go back to the very basics.
Okay, so it all starts with electric charges. And you can think of them kind of like tiny magnets. They can push or pull on each other right across empty space. We call that the electric force. You get two positive charges together, and bam, they want to fly apart. But a positive and a negative, they're drawn to each other. This whole invisible game of push and pull, that's the foundation for everything we're about to talk about.
Right. So what happens if you try to force those two positive charges to get closer? Well, you've got to push against that natural force that's trying to shove them apart. And that push, it takes effort. It's not free. In physics, we have a name for that effort. We call it work. You're literally spending your own energy to move that charge where it doesn't want to go.
Okay, so you've put in all this effort, you've done all this work pushing that charge, but where did that energy go? It doesn't just vanish into thin air. Nope, it gets stored inside the charge. It's kind of like when you compress a spring. All that energy you used to squeeze it is now just sitting there, held in tension, waiting for a chance to pop back out. And the absolute best way to get this is with an analogy we're all familiar with.
Let's just talk about gravity for a second. When you lift a ball off the ground, right, you're working against gravity. And that energy you used gets stored in the ball. We call it potential energy. The higher you lift it, the more potential energy it has. Well, guess what? It is the exact same idea with electricity. When you push a positive charge against an electric field, that's just like lifting that ball. You're storing energy right in the charge.
And that stored energy, it has a proper name. We call it electric potential energy. You see, just like the ball's potential energy is all about its height, a charge's electric potential energy is all about its position inside that invisible force field. It really is all about location, location, location.
Okay, this next part is a really big leap, so stay with me. So far, we've only talked about the energy that a specific individual charge has. But what if we didn't have a charge? What if we just wanted to describe the space itself? How could we sort of map out the potential for energy at any given point, even if there's nothing there yet?
We do it with this new idea called electric potential. And the analogy is perfect. Instead of talking about the energy of one specific boulder sitting on a mountain, let's just talk about the altitude of the mountain at that spot. Electric potential is exactly that. It's the electrical altitude of a point in space. It's a number that tells you how much potential energy a little test charge would have if you decided to drop it right there.
And here's the punchline. That electrical height, that electrical altitude we've been talking about this whole time, we measure it in a unit you already know. Volts, that's it. So when you see a 9-volt battery, what it's really telling you is the difference in electrical height between its positive and negative terminals. It's describing the energy landscape that it sets up.
Now, if we're going to think about potential as height, well, then we can draw a map of this invisible landscape, right? You know how on a topographic map you have those contour lines that connect all the points at the same altitude? Well, electricity has the exact same thing. They're called equipotential surfaces. These are lines or surfaces where every point has the exact same voltage. And what's cool is that moving a charge anywhere along one of these surfaces takes zero effort. It's like walking perfectly level along the side of a hill.
Okay, so we've built up this idea of a landscape with electrical hills and valleys all over the place. So what happens when you put something on it? Well, just think back to our ball. What does it do on a hill? It rolls down, right? Of course. It naturally moves from a spot of high potential energy to a spot of low potential energy. It doesn't need a push, it just goes.
And that is exactly what happens with electric charges. A positive charge will naturally roll downhill, electrically speaking, from a place of high potential, that's high voltage, to a place of low potential, or low voltage. It's a spontaneous motion, or as our source material calls it, moto spontaneo. And that simple idea, That's the engine driving literally every electric circuit. And this isn't just some abstract theory either. This is real-world tech. Think about an old-school tube TV. It used something called an electron gun, or cannone elettronico, and all it did was create a huge potential difference, a really, really steep electrical hill. Now here's the twist. Electrons are negatively charged, so they do the exact opposite of our ball. They spontaneously shoot up the hill, flying at insane speeds until they slam into the screen and make it glow. That's how you got your picture.
All right, so let's connect the dots. We've established that the height of our landscape is the potential, what we measure in volts. So, what about that electric field we talked about way back at the beginning? Well, the electric field is just the steepness of the landscape. That's all it is. A strong electric field means you're on a really steep part of the hill. A weak field, you're on a gentle slope, almost flat.
So, let's just do a quick recap of the whole analogy, a little cheat sheet. The altitude or the height, that's our electric potential, measured in volts. The steepness or the slope of the hill, that's the electric field. The flat contour lines you can walk along, those are the equipotential surfaces. And the ball rolling downhill, that's just a positive charge doing its thing.
Okay, let's use that landscape analogy one last time, because it explains something really important. Imagine you go for a hike. You walk up a bit, you go down into a valley, you walk around in a big loop, and you end up right back at your car where you started. What was your total change in altitude for the whole trip? 0, right? You're back at the same height. Well, the exact same thing is true for an electrostatic field, and this idea leads to a very formal principle in physics. It's sometimes called circulation, or in the original Italian source, circitazione. It sounds fancy, but all it means is that the total change in potential, or voltage, as you go around any closed path is always 0. And because of our simple little hiking analogy, this once complicated rule suddenly makes perfect intuitive sense. Of course you end up at the same height if you walk in a circle.
So, in the world of static charges, you can't get free energy by going in a loop. The field is conservative, meaning you always end up back where you started. But that leads to a really cool question, doesn't it? What happens when a field isn't like that? What if you could move a charge in a circle and have it come back with more energy than it started with? Well, that's how you generate electricity. And that is a whole other story for another explainer.